So, I thought you go back and start with the definition of polynomial.
So polynomial, many terms, there we go. So for the recording, many terms. So what are the rules for this then? So the exponent has to be a whole number, right? The exponent can't be negative and it can't be anything other than, it's got to be 0 or a positive integer. That's it. Can't be a fraction, can't be irrational, obviously can't be imaginary, none of that crazy stuff. They just have to be whole number exponents. Like for example, if we look at this simple example right here, this is a polynomial. If we want to be specific, we'd call this a trinomial. How come? 3 terms, right? If we look at the first rule, what are the exponents? So each term has a power of the variable. That's a 2. What's this one? 1. A 1. What's that one? It's a 0. Yeah, we don't write it, but there's an x to the 0 there, isn't there? It fits the pattern. Anything to the 0 is what? 1. Okay, so that's why that one just disappears, right? But we are following our rule. Each of the exponents are whole numbers. And then the other thing is that the coefficients have to be real. But they could be any kind of real number. They could be irrational, could be pi, could be square roots, they could be fractions. They don't have to be nice, neat integers like these are all written. But usually a lot of times the polynomials we work with, typically we do try to, well, we don't always try, but we find ourselves working with integer coefficients a lot. It doesn't have to be that way though, okay? We just cannot have imaginary numbers. Okay? But anything else is fair game. Just no i's, but anything else is fine. So these would be binomials. How come? 2 terms. And then a monomial is just a single term. So for example, if we were to factor this expression, factor out the greatest common factor, we usually talk about that as being a greatest common factor. It is a greatest common factor, but we can also think of it as being a monomial factor, right? Typically it's going to be, unless it's just a constant by itself, and then we don't worry about it. But if it does have a variable in there, if we're able to undistribute some power of a variable, we end up with a monomial factor in that case, right? 1 term. Mono means 1. All right, so if we want to be a little more general with a polynomial, this is how we'd write it, like in a textbook. This is how you'd see the most basic form of a polynomial. So what does this mean? This probably looks like gibberish at first, right? But I want you guys to start to get used to understanding how we can express things in purely mathematical forms and taking the time to think about what this really represents, right? So if this is a polynomial in standard form, first of all, how many terms are there in this polynomial?
5, or maybe 6.
No, it's not 5. And what tells us that it's actually not 5?
Oh, the exponent.
A dot, 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 the ellipsis. What's that mean when we see a dot, dot, dot?
Imagination.
It could be a lot more, and it means, and so on and so forth, right? We're just following this pattern, right? We got a pattern here. So now, stare at this again. Now I want you to tell me, based on that, and we'll talk more about this, but can anybody tell me how many terms are there in that polynomial? I mean, it's not necessarily. In fact, probably not. Say it again. 5 or more. Maybe there might be 2.
I think 2.
But in general, if we look at this, you're not going to be able to tell me an answer that's going to be like a precise, exact number.
5 or more, possibly 2.
5 or more, possibly 2. Correct, but not specific enough. Well, I don't want something like that. I just want you to tell me it's not going to be a number. But you can look up here, you can say, there's blank terms, and it's going to make sense. Okay, close. It's going to be n plus 1. How come? Okay, yeah, let's look at why there's gonna be n plus one terms here. Let's look at why that is. So let's just take one of these terms, like let's just take this guy, right here, for example. Okay, here's a term in a polynomial. What's the coefficient of that term?
A2.
A sub 2, right? In math, we'd say that's a subscript, so we'd say A sub 2, right? And whenever you see a subscript in math, what is it that subscript is doing? It's different than an exponent, right? It's not doing anything mathematical like this is. The exponent 2 there is telling us the x is being taken to the power of 2, right? That means something mathematically. What does the subscript 2 mean, you think?
It's different than the other a's.
It's different than the other a's. Yeah, it's just keeping track. It's an index variable is what it is. It's not actually doing anything mathematically. It's just keeping track of which coefficient goes with which power of x, right? So if we look at this, we've got a sub 0 times, technically it's time, whoops, you got it? Times x to the 0, right? We don't write the x to the 0, but we know that the coefficient a sub 0 is the one that goes with the 0th power of x. A sub 1 goes with x to the 1, right? A sub 2 goes with x to the 2, a sub 3 goes with x to the 3, etc. All the way on out to however many terms we've got, right? So we're going to go through a bunch of these. The very last term we're going to call the nth term. That's going to be the biggest power of x, is x to the n. Okay? Well, that means that the coefficient of the biggest power of x we're going to call a sub n. What is n? Who knows? It might be 100, it might be 1,000, it might be 2. Right? It depends on the polynomial you're working with. But n is what we call, we give that a name though. N equals the degree of the polynomial. So if we're talking about a 7th degree polynomial, then we're talking about a polynomial whose biggest power of x is x to the 7th. Okay? These are all the coefficients. What do we call a sub n then? If it's the one that's, when we write a polynomial in its standard form, you notice that the powers of x start big and they incrementally just get smaller until they fizzle out at the end and you just get a constant at the end, right? So we always want to place them in that kind of decreasing numerical order, the powers of x, when it's in standard form. So that means that a sub n is kind of a special coefficient because it's the one that's out in the lead. It's the one that comes first, and so we call that, oops, what?
Holy, thank you.
So we call it the leading coefficient. And why do we call it the leading coefficient? Because it's in the leading term. First term is the leading term. Okay, make sense? Yes, sir.
So the coefficients have, sorry, not coefficients, the exponents, they have to descend by 1 every time?
Well, yeah, they do. They do. I'll give you an example. Like, so for example, what if we've got, we'll make a polynomial up. What if we've got f of x equals 3x to the 7th minus pi x to the 4th plus x minus e, where e is just it's another natural constant, it's the natural number. Okay, they do, they descend by 1. The leading coefficient is what? 3. So we'd call that a sub 7, right? What's a sub 6? 0. It's missing, right? So that coefficient must be 0, okay? We have 0 times x to the 6th because there is no x to the 6th term written down. It's there though, right? We just don't write it. And we get 0x to the 5th plus negative pi x to the 4th, right? So in answer to your question, I guess it's kind of a yes-no answer. I mean, we wouldn't write those, so you could look at this and going by the rules, there are those extra, right? I didn't say it. I didn't say it. If we follow the rules, we actually do have an x to the 6th term there, but it's just invisible because the coefficient is 0. So in practice, we can skip some terms, right?
I think you should just say technical.
I'm not doing it. So what do you suppose we call this term at the end, which may or may not be there?
Ending term.
But is there an x that goes with it? I mean, there is. It's x to the 0, but x to the 0 equals 1.
So just call it 1.
So it ends up being a number without an x?
Yeah.
So what do we call that probably? It's a constant. There you go. Okay, makes sense? So you get the idea, right? Okay? So we've got these polynomials, they're term by term. This is how we would represent a generic polynomial. All of the a's are actually numbers, and all of the, n is going to be some number too, right? That's the base power of x. So what do we do with these things? Well, we're just going to walk through how we do arithmetic with them today. It's really simple. If we look at something like this, we've always called that a quadratic function in standard form, right? And it is, but what is it also? It's just a polynomial, isn't it? Right? It's a trinomial, right? It's a third degree polynomial. What am I going to do if I'm adding up polynomials?
Combine like terms.
Combine like terms, that's it, right? That's all they do is combine like terms. I'm not even going to go through the example. I'm going to combine the x cubes, combine the x squares, combine the x's, combine the constants. No, I don't need to. You got it. We'll do this one instead.
Oh.
Yes.
Okay, this, technically, sorry, I said it again. It is, I gotta just strike that word from my vocabulary. It is subtraction, you might say, but isn't subtraction really just addition? You're just adding negatives, right? So how do you suppose we would go about simplifying this expression?
Slide those negatives out.
Yeah. Right, so you might be tempted to subtract like x to the 4th, 1x to the 4th, or 9x squared minus negative 5x squared, and figure out what that is, and then I guess there's no x squared there to subtract. But don't do that. Instead, always just distribute the negatives and then add them up, combine like terms. Right, so we'd end up with x to the 4th plus 9x squared minus 9x plus 1. If I distribute the negative, what am I going to get? Plus 5x cubed plus 5x squared plus 10. Oops, to the 4th, not the. Minus x cubed plus 8x plus 5, right? And then what do? Combine like terms. So let's talk about just pragmatically here. How do we do this without making mistakes? So I could just combine terms and then cross these off as I go. Do you see that this is sort of a disorganized way of doing it, though? A little bit? I mean, because polynomials, in reality, you might have many polynomials you're combining all at once. They might be very large polynomials. Writing these out as a string, it makes it hard to just search through there and find all the x squares. And I mean, what if there are 14 of them, right? And that's going to be hard to do. And you might get, in some cases, you might be adding up lots of polynomials. So do you have an idea, anybody have an idea about how maybe you could organize this in a way that would be easier to keep track of and in which you'd be less likely to make a mistake?
Line them up, tallest to shortest.
Well, I mean, kind of. That is kind of what we do. They don't necessarily have to be tallest to shortest, but we're going to line them up vertically. Yeah, we're going to line them up vertically because when we add like terms, and listen very carefully to this because we're going to come back to this idea again and again. When you're combining polynomials, we want to reserve a column for each power of x, right? So what we can do instead, like let's make this one, this will be our green polynomial, right? So if I want to add all these things up, I could do x to the 4th, there's my x to the 4th column. I skipped an x cubed, so I'm going to leave a space there, right? I don't have to write 0x cubed. I could, but I don't have to. But I'm going to leave space for an x cubed, and then I'm going to move over to plus 9x squared minus 9x plus 1, right? Now I'm going to distribute the negative sign, and I can do this all at once. I'm going to distribute the negative sign and then just add the result, right? So what's that going to give us? We already told me I'm going to get a positive 5x cubed. I'm going to get a positive 5x squared. I'm going to get no x's, and I'm going to get a plus 10. You're starting to see the logic in this probably, right?
Oh, yeah, I see it.
If we distribute the negative there, I'm going to get a minus, oh, bad color.
Oh, too bright yellow.
I'm going to get a minus 8x to the 4th minus x cubed. Skip over to the x's and get a plus 8x plus 5. And you see the benefit, right? Now all I have to do is just add vertically. And I keep track of all the like terms that way. You can see that you're much less likely to make a mistake that way. So we end up with x to the 4th minus 8x to the 4th is negative 7x to the 4th. 5 minus 1 is 4x cubed, 14x squared, minus 1x, and then 16. There it is. There's our answer. Right? Okay. From there it is no biggie. You're right.
That's just teeny.
Okay. It was, well, okay, yeah, what would that have been? I mean, at some point, that's that's what we call a quartic polynomial. But do you need to know that? No,
Absolutely.
you don't. It's a 4th degree polynomial. It's fine.
What if it's got 5?
Did that come from Spanish?
But it's the power of x is 4, right? If it's squared, we call it quadratic. If it's cubed, what would we call it?
Triadic.
What do you think we call it?
Third square.
We call it a cubic polynomial because the x is being cubed. Okay? It's a, yeah, okay. So I see what you're getting at. Like we called this a trinomial.
Pardon the interruption. All ASB and class officers should be getting their 8th graders out to the buses immediately.
So I see what you're getting at. So let me get attention, please. So if you're going by the number of terms, I don't even remember what it's called. I don't. But you never would say those things. All you're really going to say, you'll talk about maybe trinomials, but after that you're just going to talk about whatever the degree of the polynomial is, right? And what's more important than how many terms there are, and think about this. So this is a binomial, right? But what's really more important about that is that the biggest power of x is x squared. 0 is a number just like every other number, and so if we're missing a term, all that means is that we've got a 0 coefficient in there somewhere, right?
So you call that not accurate.
I mean, it's accurate, but it's not important. I mean, it's like a lot of times we talk about binomials because we're going to do binomial expansions. One of the things, so here's where we're going with this, like in the next week and a half. We're going to do some stuff like this. Like we're going to want to know what happens if we take a binomial of the form, something that fits the form like a plus b, and that's a is going to have an x in it, and b may or may not have an x in it, and we take it to some power. So we want to multiply it by itself a whole bunch of times. Are there some patterns that we can develop where we don't have to go through that arduous process of like multiplying it out and then distributing again and distributing again? Yeah, there are. There's some expansion patterns for binomial polynomials, right, with 2 terms. So in that sense, it's important to know that it's a binomial. This is a trinomial. We talk about trinomials because we've got trinomial factoring patterns. But other than that, we really don't talk about the number of terms. What we talk about instead is what's the power of x. So we would say that this is a quadratic polynomial because the biggest power of x is x squared. This is another quadratic polynomial. That's a linear polynomial because the biggest power of x is 1. And if the biggest power of x was 3, we'd call it a cubic polynomial. If it was 4, we'd call it a quartic polynomial, right? So that's more important to know that stuff. And I'm not even going to spend any time on it today. We'll get back to it later, but that's not a big deal. I want to That's not math-related stuff, it's just kind of taxonomy. It's not really important. So let's talk about, then, how do we multiply polynomials? So I want to go back and kind of unteach something that you were taught in previous years. And it served its purpose at the time, but we always talked about FOIL, right, when you multiplied out binomials. And it's fine, I mean, it works, it's no problem. But really, multiplying out binomials is just a general case of multiplying out polynomials. And so really all you do when you multiply out polynomials, as you already know, is you're just going to distribute from one factor to the other factor. Like in this case, we would be distributing from the first factor over the second factor. That's how we'd say it in math. We're going to distribute 2x plus 3 over 3x minus 5, meaning we're going to distribute the 2x to both terms, and then we're going to distribute the 3 to both terms, and we'll just add up whatever we get from that, right? Okay? So let's take a bigger one. Here's a harder case of the very same thing, right? Is there a preference which one you distribute? It's going to work the same either way. My preference is I would always choose to distribute from the polynomial with a lesser number of terms, because then you actually have to do fewer distributions. But it'll work the same both ways. And I think when you see how we're going to organize this, you'll kind of see why, yeah, it probably makes a little more sense. So let's do that. Let's distribute from the trinomial over the larger polynomial with 4 terms, right? So we'll distribute the negative 6x cubed. First thing we're going to do. And what's that going to give us if we do that? Okay. So what's the first thing we're going to get? We want to distribute to the bigger powers of x first. So negative 6x cubed times negative x to the 4th is positive 6x to the 7th. Is it possible to get a bigger power of x out of this? Is it, when we're multiplying this out? No, we got it, right? Because both of these polynomial factors are written in standard form, right? So we know that when I take the product of the leading terms, that's going to give me the biggest possible power of x. What's going to be the smallest power of x in this process? 0, because I'm going to multiply a 6 times a negative 1, and I'm just going to get a number, right? So then how many columns am I going to want to have when I want to add up all the like terms? 8. I'm going to get 7
The
plus
last
1
call
for
for
the
8th
constant,
graders
right?
to get out to their buses and get loaded to go back to Sunrise Middle School. 8th graders, get to your buses immediately.
So you guys just help me. I don't want to think about this. You have it all ready to go. If I distribute the negative 6x cubed to the positive, to the negative plus 24x to the 6th
Negative 36x
to the 4th. So I got to skip a column, right? So I'm going to skip a column, and I'm going to get minus 36x to the 4th. Then what?
6x to the 3rd.
Okay? So now we'll distribute the x to everything. What's that going to give me?
Negative x to the 5th.
Okay?
Negative 4x.
6x to the 2.
Okay?
And 1x, negative 1x.
Okay, so minus x. Okay, if I distribute the 6 all the way through,
Negative 6x is 1. Negative 4x to the 3rd.
Yeah, where's your lever at?
This is 17.
I don't know. It's always down there.
Oh,
Now what? Right, and then finally,
Negatives.
oops, I messed that up, 36.
You really want to be tedious, you can fill in zeros.
But I don't want to be tedious.
Gosh.
then what would I do? Add them up. So yeah, you see now why when we're multiplying out these polynomials, and we're going to get tons of terms when we do this, that that definitely helps to keep these things lined up vertically, right? And then all I got to do is add up the like terms vertically and we're done. Yeah, I'll skip that step. There's another way to do this too. Take your pick. This is the way I typically I do it this way. But there's another way that you might like. We can also do this. We could do something like if I'm going to multiply this polynomial times this one, I can write these both out with including zero coefficients. So I'm going to leave spaces and I'll actually write the zeros this time. So I've got a 5x to the 4th minus x cubed minus 3x squared plus 0x minus 4. Okay? We're going to multiply that by this guy. Now I'm going to write this one vertically over here. Have you seen this? Have you guys done this before ever? No? Okay. I don't think you probably have. So I've got a minus 6x cubed. I'm going to also leave rows for every power of x.
Like a multiplication.
Exactly. I've got a plus x squared. I've got a plus x and a plus 0. Okay, and look what happens. Okay, so what do you think? We're going to look for patterns here, right? So if I multiply these out, negative 6x cubed times positive 5x to the 4th is negative. Okay, negative 6x cubed times negative x cubed. Okay. Negative 6x cubed times negative 3x squared. Right? And then finally I get
X cubed.
okay, so what color goes there?
I don't know what the colors mean.
Oops, hang on. There we go. Right? See what I'm saying? This time, when are we out of here? 11, oh boy, okay. So you're going to see the pattern, right? So this time we're going to get all of the like terms are going to line up on the diagonals if you do it this way. So then we get x squared times negative 3x squared is whoops, sorry, I got to go here. I'm going to get minus x to the 5th. And then I'm going to get, that should have been different colors, shouldn't it? Well, those should have both been different colors.
Yeah, it's gonna stay.
Or what I was doing.
I don't know what you're doing. Get some magenta.
Yeah, we got to get something different going.
Skin color. Skin color.
So what am I going to get? Minus 3. Get the idea?
Yeah.
Keep going. You got it. You got it.